Hi guys, welcome to the Data Science Mentor session. And my name is Pablo. I am a data science professional and the founder, host, and convener of the Data Science Mentor program. We are teaching fundamentals of data science that will guide you in the future of machine learning, deep learning, AI, and all. But this is the beginning, and the beginning is super, super important. Now, what makes data science mentor really different is we bring mentorship as a service, example as a service when we teach. And I think these two components are super, super important when you're getting folks to learn from scratch. So yeah, so this is our session. Sometimes we stream our sessions. When we stream our sessions, gives other folks the opportunity to know that the Data Science Mentor program is live and kicking. And so this is one of the sessions. So if you're fortunate to see this session on, feel free to drop a message in the comment section. Let us know if you're interested in the Data Science Mentorship program, and we'll let you know how to sign up and join. Right, today we are going to be talking about the final part of regularization. Regularization is typically for a very simple way, regularization is called a penalty. If I was to define regularization in a technical term, I will say it is a penalty for coefficients, right? But that's most times that's really some big statement. So in an intuitive way, regularization is the nudge to your model to stop overthinking. It's when you overthink things. In life, we overthink, right? If you have an exam to take, you start to, instead of focusing on the exam and saying, look, I'm going to use my practice questions. And when I see new questions, I'll be able to answer them, which is what machine learning models do. They see training data, which is historical data, and use historical data to predict new situations or to make predictions on new data. So that's basically the analogy. But sometimes a model can overthink. It's a thing, just like humans overthink, models can also overthink. And when a model overthinks, you need to punish the model. And so punish is not the literal punishment. What is it? So what models do basically is they give a certain weight or number to something they're going to use to make predictions. And so if they overthink it, you can basically do your job is to tune down your overthinking. So that's what regularizations are when it comes to models. And so we'll be doing a final push on this. So this session we'll be looking at linear regression, and so we're going to basically look at this and then go ahead. But we're going to do a bunch of things, and hopefully we can just start from scratch and wrap it up. Right. The reason I'm talking about a wrap up is because I'm going to bring everything we have been doing, and then I'll just wrap everything to a final point. But if you check out the other sessions, like session 21, 2019, you see that we did some intros. And so today is like a final part of that wrap up. Now, to get started, I'm going to do a few things. I will first import, which is bring in two things. Matplotlib. Matplotlib is a library for visualization. I am also going to import NumPy, which is for numerical computing. We also use that for data analysis, where you use it to convert data features to numbers, and numerical analysis pretty fast. That's what it is. So this is NP. One more thing, I would want to should I? Yes, I'll say plt dot style plt.style dot use, which is a way to give your background. It's a way to give your background sort of like to give the backgrounds of your charts to look good. So it's a style sheet. So I like to typically look at it. So it's a style sheet, and with this style sheet, you can make references to the kind of, you can choose the kind of background you want, right? So there's a style sheet. So I'll take a certain background. You can see that there are different backgrounds. So I could take a certain background and say, okay, this is the background I want to use. So you can see the different backgrounds, right? So you can see the different backgrounds. Yeah, okay, I'll use this Seaborn, yeah, because it has grids, and I think it works a bit. Now, another way we can do that is to basically say plt dot I think style dot available. Yes, and then with that, it will show us what we're looking for. So we had our Seaborn. I think this is it. It's the white grid. So I'm going to take this. So this is what I'm going to use. So I'll just put this here. And so this is what we're going to use. So with that, any visual we have, we'll have that. Now, one of the things we want to do whenever we build a linear regression model is we want to look at data. We want to use this linear idea, this idea of bringing models, finding how to predict models with the relationship they have. And if the relationship has a linear relationship, sort of makes it easy. But and with that, we can just pass a line. It's called the line that best fits between the observed features and the predicted feature. And then we can now know how well we can predict stuff in future. So that's basically what it is. So to get to talk about that, I'm going to generate data and then use that to describe what we're doing. Again, this is like a wrap up, right? So I'll start off by, I'll use this. This is often used, random number generator. That's what it means. Then I'll say I'll use NumPy, and I'll use NumPy and say np.random state. So this, we can use any number at a random state. I could use 42. So which means if I use 42, it means at any point, if you want to replicate what I've done, just use 42 and you can get the same results, right? Just to reproduce it in a way. So here I'm going to use X here, and then I'm going to create random data points. I'll try as much as I can to, when I'm creating these random data points, I would ensure that they have, it's random, but at the same time, it has like a normal distribution in a way. So here I'll say 10 times RNG, which is this guy that can use to generate numbers. And I'll have rand. If I check, if I say np dot random dot rand, look at that. That's what I'm doing here. You can see it's random values in a given shape, right? So this is what when you see me use this, I have already packed np.random inside this, so I don't have to use it anymore. So I can just say .rand. So I'll have like 50, see that, and I'll multiply it by 10, right? So random values in that state. Then I'll create y. Then I'll call this 2 times x, so 2 times this. So which means I'm doubling the way this guy is going to look. So at the point you can see that it will start growing in the way. So I'll say 2 times this minus 5 times, not times, plus RNG dot random rand n. Now again, when I say rand n, if I come here and I use this, it will tell you it returns a sample from something called a normal distribution, and a standard normal distribution will just show you like 68% of your data is in a symmetrical shape, so to speak. So you would find a bunch of, it's a convenient way just to create distributions, and you're going to see it when we visualize it. So this is what I'm going to create here, and I'm also going to make it 50. Then I'll go on to use PLT dot scatter, which is, I'm calling PLT from this here, which is for building visuals. Then I'll call on these two guys here, and I'll go on to say PLT dot show. So it will show me what it has visualized. So you can see what has happened here. You can see that. So this is typically the data we have. Right. Now, what we want to do is with a linear regression model, you can try to fix a model into this and just make it be able to find out if there's some sort of like a way you can make predictions, understanding this data. And if it does understand this data, then if you give it new data, it can try to make sense of it. So that's the first thing we want to do. Then, so the next thing we will do after showing this is we're now going to build a model and then create like some new data points, right? And then visualize them, and then see if once we create this new this data points using this existing data we had created, if we can put a line that best fits in between. And that's a part of where all we're doing is we're heading to regularization typically. So the next thing I'll do is to use a linear regression estimator. That's like a linear regression model. So here I'll call it a linear regression estimator. Now with this, I'll import, it's called model class. I'm going to import the model class. So this is sklearn dot linear model, and I'll import linear regression. And then this is the first thing I do. And then next, I am now going to put this model here. I'll instantiate it and put it inside this variable called model. So I say linear regression, open it. I'll use fit intercept true, which is a concept that basically lets you know the starting point of your different features and how you can use it to do predictions. So the starting point basically most times is to tell you stuff like, if I was to start at 0, if X was to be 0, what is typically would my Y be? If you were to take an Uber trip, if you were to take a trip on Uber, what would be your base rate? So something of that nature, right? So I use this. So I now go on to do stuff. I'm going to now say model dot fit. Then when I open it, I'll use X, which is the first stuff we created here. And now this is also part before just for the benefit of those who were not in our offline mentorship session, we talked about writing simple code and sort of like using it to understand what you're doing when you're abstracting problems to Python. So here we have X. Now we're going to put a square bracket here. Now inside the square bracket, we're going to slice X and say we want a new axis. A new axis is like saying, give me like a new dimension, right? and then I'll have Y. So in essence, what it will do is, because if you have a data set and you need to, and I have mentioned this in our former class, in the classes, and if you're signed up to the data mentors program, the data science mentor program, you would have seen where we talked about the data representation for the scikit-learn APIs. So that's what we're trying to do here. So we want to set up in a way that there's a feature matrix, which is n samples and n features, or n features and n samples, and there is the target variable, which is just samples. So we run this. Now what we're going to do, I'm going to call this x fit, which is I want to see how we can fit our model. So I'm going to create sort of like a new data point, and then go on to visualize this new data point with respect to our existing data. Then this fit intercept is a line that will just come through, just to show us how our observed data and our new data sort of come into into perspective. So with xfit, I'll say np dot namespace. This is basically saying, look, I can return evenly spaced numbers, right? And so I'll say 0 between 0 and 10. Then I need like 1,000 of them. Then I'll call this y fit, and I am now saying model dot predict, and with that I'm going to take x fit, and I'm still going to, just like I did in the bits, I'm going to now say np dot new axis, np dot new axis, and then I'll have that. Then with this, the next I'm going to do, I say plt dot scatter, and I'm going to take x and y, and I'm going to now say plt dot plot on top of the scatter plot. That's what I mean. And then I have x fit and y fit, and then I go on to say plt dot show. So it's supposed to show us this. So you see, now I've introduced, like, you see why I did some introduction, just like this was initially here. So I sort of like did an introduction with the data, and then sort of put a line in between just to say, look, if the first data point was our the observed data we have, and then we now have a new data we have predicted, can we pass a line through it to see if there isn't a difference between there isn't much of a difference between the observed values we had in the past and then what we have predicted with the data we haven't seen. Now, this, my people, can be really this is where we start to have some conversation. Now, data doesn't always data doesn't always behave this way, right? Data doesn't always behave this way. What it means is sometimes you would, the things that happen when you build your data points is your data points will behave. The things that will happen when you build a model is that your data points may not behave the way you expect them to behave. They might not be linear, right? And so how do you deal with a situation where your data point isn't linear, but it follows like a curve? And you are using a linear, you're sort of like using a linear regression model to make sense of it. Now, this is the first part of it. So now with this, we are now going to go into something called a polynomial regression function. So what it means is the polynomial regression function, right? They're often called basis function. Is it will find the non-linear relationships that exist and then go ahead, to find the curves that exist in them by introducing a dimension to the features you have. So you see all these features. In case we have a non-linear model, how do we deal with it? So that's basically the question at hand. If we have a non-linear model, how do we deal with it? So that is a question here. So the question here is, if we have a non-linear model or a non-linear relationship, what to do? So this is where we are at this point. And again, like I mentioned, we have talked about this in many ways. So what we are going to do is we're going to introduce something called a polynomial function, and it is a way we can tune our model. We'll tune our model in a way that says, look, once we tune our model and we visualize our model, right, we can make sense of the different situations that exist in our data. So that's what we're going to do. We're going to make sense of it. So here we will introduce a polynomial basis function. So this is a polynomial basis function. And I'll show you what a polynomial basis function does. Now, so the first thing we're going to do is we are going to illustrate it, right? And then go on to see what it means. So what I'm going to do is I'm going to generate data, but once we generate the data, we're going to generate the data, something that looks like the last data we generated, right? But we're now going to fit it with a polynomial function. And when we fit it with a polynomial function, what happens is the data will now search for weird things that exist, like curves. They'll search for curves, right? And so that's what I am going to do. So in essence, we just want to fit a complicated model. So I will do this. I'm going to say from sklearn from sklearn.preprocessing, I will import polynomial features. That's one. Then I will say from sklearn.pipeline, I will import makePipeline. Now the makePipeline makes it easy for us to basically create a very simple and efficient way to build our model that makes it really great. And we'll just plug in our linear regression, plug in our polynomial function that just helps us tweak and find those non-linear features that exist. So that's what we will do with that. Now, to this end, the first thing I'm going to do is I'm going to create a pipeline that contains it. So I'll call this this is going to be like a polynomial underscore model. Let me call that this. Now with this, I'm going to say make pipeline, and inside I will have the polynomial features, and I'll say this polynomial feature, tweak it 7 times, right? Just to figure out if there's anything that's weird in our data. And we're also going to also have our linear regression model inside. This model basically finds out relationships. Now, when with this set out, we are going to generate the random data, and then we'll fit this random, and this random data will generate would make this random, one of this random will create the feature, and then the data we are to predict will make it have a wave. We'll make it have a wave. And how do we make it have a wave? Remember the sine, cosine, those are like waves. So we would make the data have a sine wave. And if it has a sine wave, then that tells you that the data is not linear in any way. It's sort of have curves. And then you now wonder if it can predict with all the curves. So that's what we're going to do. And that basically tells you what we are trying to achieve generally. So again, I'll generate the data just like I did here. So I'll generate just like I did initially. So I'll generate data. So what we do is, again, RNG to our rescue. I'll say RNG MP random state. Let's still use 42. Let's maintain, see that stuff I've been trying to do, just maintain reproducibility. I create X, and just like I did before, I say 10 times RNG.rand. I see 10 times RNG.rand, say 50 elements. But our Y, with our Y, we're going to say MP.sign. So you see, with MP.sign, we're going to use that trigonometric function to create that, right? So it's going to be like a sign. So when we put X in here, it's going to take this guy and sort of like form a wave out of it. And then we'll just add a few things to it. We can just make a few calculations to it to add something like a little bit of, well, I call it noise, a little bit of, it's just like to jiggle the data, so to speak. So I say RNG dot rand, and I'm gonna say 50. So now you see we have two data points, just the regular one and this one that has like a sine wave. And just to put it in perspective, when I say sine wave, if I write a sine wave and I put an image, you can see that an aspect of the data will just have this going on. So that's what I'm trying to get at. So with this, I will now go on to now call my model. I'll now say my polynomial model, I want you to fit into this X data. And MP.new axis, which makes it have like again n features and n sample. Then on the other end of it will be our Y. Now with this, I will now come down here and say Y fit. This is we trying to do some predictions now. So we say with our polynomial model, do a prediction, and I want you to do a prediction where we are going to use X. We're going to use, because we had created this kind of data before, remember our X fit and Y fit, right? Because this has been introduced, you can see that the X fit and Y fit were like this, and now we have introduced the Y here, and this Y now has it's like a sine wave. So what we're going to do is I'm going to say predict, and then we'll just put both data points together. You will see that on one end, the model is going to try to, first of all, look at the data points and look at how we have introduced them and try to make them act weird. right? And then see how well the model tries to find, make sense of it. So here we say X fits, and again, put this np.new axis, right? Then we can now say plt.scatter, and on top of each other we have X and Y, remember? And then we now say plt.plot, which now tells us that we can plot on top X fits, yes, X fits, which is the older data we have, and Y fits, which is what we have here, which we've done a prediction on them. Now, we can now say plt dot show. Now you can see that because of the introduction of this, we would you can see that some of the data, they are now all over the place, and because our Y, which we have our observed data, which is X, and then our Y has now, we've introduced this to it, right? We have introduced excuse me, we've introduced some kind of like a wave to it. With this, you can see that it tries to make sense of these weird situations where the data isn't linear. Now, with this situation, I don't want you to just think that it all ends here. It doesn't. Now, think of a situation where you are trying to predict a linear situation where, let's say, you want to predict how fuel is consumed in a car when the different levels of speed, right? Now, you can understand that cars have different ways with different drivers and how they will typically drive and different terrains and all. So you can't basically say, the higher you put the engine and it just starts to burn the fuel. Some engines act differently, right? So you're typically trying to predict that. And so you are going to have different situations. Some situations are not linear, which means the more I drive my car, the more it's burning fuel. It all depends on what you do. You could just go from a place to place. Maybe every morning you go from one spot to another spot, which is pretty close. For another person, the person travels a longer distance. For some other person, the person travels a longer distance, but their cars may have a problem. Maybe their what's that one thing that regulates fuel in the car? Maybe their fuel pump has a problem. So it's the it has such a low pressure that whatever the fuel goes and it burns, it release. The car is pushing so fast, but it's burning so much fuel, but it's not giving so much speed. And for someone who has really good fuel pumps, is burning as much as it is. For a car that has really good fuel pump but has a fuel economy introduced into it, the more it takes on, it tries to reduce the amount of fuel it's burning. For a car that is typically in different shape and has maybe a ton of people inside of it, you're driving it because of it surpasses the number of individuals it's supposed to carry, then it has to burn so much fuel because of the amount of load it has, weight it has on it. And these situations are, non-linear. So to this situation, you will now see that what this is, what we have up here is a linear polynomial fit to a non-linear data. So that's what we have over here. And this is a thing. Now, hold on. This is a situation that would have. Now, additionally, we're also going to, one other part where we talked about is, but what if we now have a situation where we have data that there are many ways we can have a linear fit, we can have we can use polynomial features, we can use Gaussian features, right? But sometimes, right, we may have a situation where this data understands these things going on, where the model understands this, but then it calls into question a problem. Because if your model can understand all these intricacies, if your model can understand all these intricacies, it's going to lead to something called overfitting. Because the model will understand its training data so much, but when it sees new data points, it's all over the place. So this is where regularization comes in, right? This is where regularization comes in. And with regularization, what we do is we sort of penalize. That's what we do. We penalize a lot of the problems that exist in it, right? And that's the part where we have talked about earlier on in our last class, where we talk about the penalization using. See, we talked about them earlier on when we talked about this. So what I'm going to do is I'm just going to quickly just run some bunch of codes, right? And sort of like try to make sense of and just build a bunch of things that would help us make sense of what we call, it makes sense of regularization in itself. So we would have to build something. Now, the first thing we'll do is, since we talked about the polynomial function, we're also going to look at a Gaussian feature. We talked about the polynomial features. We talked about the Gaussian features that sort of like thinks about data in a normal distribution, but sometimes a normal distribution that has curves. And then we would see how it will try and fit that in. So yeah, so that's what we're going to do. There's going to be a bunch of codes. But what I'm going to do is I'm going to create, what we're going to have is something called a uniformly spaced Gaussian feature. So that's what we're going to do. So to do that, I will first say from sklearn, and feel free to drop off at any point. If you're on the live session and sort of like we're past the time, feel free to drop off, and you can always watch the remaining session because you have access to that. So yeah, so we have this sklearn.base, and we can import the base estimator, and we can have something called a transformer mixin. We'll introduce that. Now, what I'm going to do is I'm going to create a class. So classes basically would enable us define some attributes that would help us typically work with our data in future. So I'm just going to do that. Let me just basically copy all this. So typically what it will do is it's going to help us determine the way our inputs would look like, right? So I'm just going to copy this. So this is like this is basically we're creating like a uniformly spaced Gaussian feature. So that's what this is. In essence, you're going to see us make use of that. You're going to see us make use of it in a bit, right? it is just going to return us like it's going to return us like a distribution that shows a sort of like a normal distribution, even though our data is kind of sort of like a wave. Now, what we're going to do is we'll now come over here. We will now come over here and now say our Gauss underscore model or Gaussian model, and we'll make pipeline, and inside we'll have our Gaussian features. So we'll say 20. We had our polynomial features then we will now introduce our linear regression, right? Then we will now go on, just like we did before. We will now see how we used a polynomial feature here. Here we're going to use like a Gaussian feature where we're going to be tuning, but we're going to be thinking of it from a normal distribution rather than a polynomial distribution. A polynomial distribution at a point takes every feature and sort of like, multiplies it by a certain number. But this one is just going to look at the distribution and follow it in a way that is like a normal distribution. And a normal distribution typically has like a symmetrical, finds like the symmetries that exist in it. So here we are going to now say Gauss model dot fit, and we're going to put X in here, the same old X that we have, and make it. We're going to make it. We're going to make it the feature matrix, which is n samples and n features. Then we're going to take Y underscore fits, and we'll take our Gauss model this time around and make a prediction on it. So we're going to predict and take X fits. Right, and here, and then do some predictions. Now, once we do this prediction, we can say, making me feel like I'm writing too much code. I'll basically come and copy this guy. I'll copy this guy here. So we have scatter plots, and we'll plot X fit and Y fit. Then we'll just create, because it is sort of like using it's different from when we created this guy. I will say, let's have a limit, because I'll say PLT dot, the x-axis is going to have like a limit, this guy, so that we don't have it just going over and over. So we say X lim of 0 to 10. Let's look at that. So if I run this, so you can see that you can see what happens. It's sort of like we just looked at how this is following like this normal distribution, right? And so this is what we have here. Yeah. Now, with what we have on this point, right, we can see that in many ways we have tuned this visual to say, okay, let us fit into the rigors. And you can see that even when we fitted it into this rigor, it feels like, it feels like it sort of like try to make sense of it, right? Okay, so what we can do is we can still use this just to see a different aspect of the model that was created. We can still use that to see a different aspect of the model that was created. But now, what we want to do is we want to introduce regularization. So you can see that not all data points act this way. So if we have an overly complex data, what now happens? If you have an overly complex data, it's the model will fit into an overly complex data like this. But when you give it new data, it's just going to be like, I don't know. So what happens? Situations like this, um, with this kind, with these situations, we are prone to overfitting. So we're prone to overfitting because the data at a point, it starts to think with all these things going on, right? How do, with all this going on, we will just have serious issues. And since it's prone to overfitting, regularization comes in to solve the problem, right? What regularization does is it is going to check. So every time you are predicting a feature, your model gives, there's something called a coefficient. Your model gives a coefficient to it and says, look, I am, for every data point, I am going to say this data point is important, and I'll give it a certain coefficient. This data point is important, and I'll give it another coefficient, right? With that kind of situation, if it gives it so much high coefficient because it's the model sort of understands the intricacies, at a point the model will start giving really wild coefficients. I'm telling you, the coefficients will become really crazy, right? And that means this isn't how it's supposed to happen in reality. And so how do you now deal with this situation? How do you deal with this situation? So what we are going to do is I'm just going to quickly show you a very quick one. So we're going to now say regularization versus overfitting. That's what I'm going to call this. Regularization versus overfitting. And so this is where we want to just get out of this sort of situation. So what I'm going to do is I am going to basically write the same code, right, that I just did here. But yeah, so but this time I made the Gaussian features 30, and then I'll say plt.show. Now here you can now see this is a situation that we have. With this, it's able to understand the intricacies of the code. But what now happens in a situation where we now want to basically plot on a model, right? So what we're going to do is I am going to create a function that should capture every coefficient of this feature we've seen here, how the model gets to calculate each coefficient, and you can see how it's very erratic in doing that. So the first thing I'm going to do is I'm going to plot a function, right? I'll plot a function that captures typically everything going on. So this is it. It captures everything going on, is a subplot, and looks at our model and how it fits in. It puts the first scatter plot and it predicts, then goes on to check for both, and goes on to check for all we have done. We have the X and then the Y label. Now, the next thing I'm going to do is I am now going to write an if statement that says, please, for every step, show us the coefficient. So that's what we're going to do. So for every step here, you get me, show us the coefficient, which is the model step 1. It will show us the center, it shows us the coefficient and all. And then with that, we will now go on to say model equals make pipeline. And then in this, we will now have our Gaussian features, just like we have done before. Introduce the linear regression. Then we can now say basis plot, which is this. We'll now plot our model so that we see how it behaves. Then once we are done with this, we will now plot dot show, and it will show us stuff. Now, what is okay, PLT. So you now see that this was what it was doing over here, just like it was. So it looked at the model. So now every time it's going through every feature, it will be determining a coefficient for every step. And then every coefficient is basically saying, I think this is important. I think this is important. You can see it's pretty erratic the way it's making changes to its coefficient. It's pretty erratic. It's basically just throwing a, from this. It started really small, then all of a sudden it's just, giving different coefficients as it goes. It drops down, comes down, because it's trying to make sense of all these rigors. And again, when you build a model this way, I mean, there tends to be an issue. Now, this is where we now make sense of it. And this is the final part, I promise you guys. Now, I'm going to introduce a technique, a regularization technique. And what this regularization technique will do is that it will tell us that, look, I am going to ensure that all these rigors we are going through, I will sort of punish this coefficients that are just being thrown all over the way. I'm just going to sort of like slow it down, right? So that's what's called penalizing it. So what I'll do is from sklearn dot linear model, I'm going to import Reg. Reg is is a regularization library, right? And so I will still now introduce model here, and I'll now say make pipeline. And when I make the pipeline, I'll call the same Gaussian feature, make it 30. However, I would now introduce reach. And inside of reach, I can now say, I can now look at the alpha here. The alpha is the one I'm going to work, which is, I'll control how it's, punishes or control how it does the, it manages the coefficient or punishes the coefficient. So I'll say alpha, I'll just say 0.1. By default, it is 1, right? I'll just say 0.1, and I'll cover this. Then I will now call on the same basis plot I created. I'll call on this model. Now, this is a different model. Remember, this was the initial model we created with the linear regression, right? And with this one, we introduced this guy to understand the intricacies, the curves that happen in reality, right? But at this part of what we are doing, I am now going to introduce, I'm going to introduce this one. I'm going to call it ridge regression. So with ridge regression, we will now have a model, but at this time it's going to use ridge. And then when we run this, we will now plot plt.show. Now, with this, you can see over here when it was finding all the curves. But with ridge, you can see that it sort of like starts to, it's become smoother. And if you look at the way it's assigning coefficients, you can see that it is assigning the coefficient with some, with some responsibility in a very responsible way, rather than an erratic way you see over here. So that's what regularizations help to do in our model. They create some kind of a stability in our model. So this is basically what it is. It creates this level of stability so that when we use a normal model and we use a linear model to predict stuff, and we want the linear model to understand the intricacies, sometimes we take a step forward and introduce a regularization model that will help us punish some of the excesses that the linear model will be doing. So that is, you know, the final roundup for it. So think about this and think about all the intricacies that come with it and the sense that goes with it. And you would realize that when we make predictions, we just don't make predictions. We also think about the situations that happen in life and how important those situations are to predicting new situations. All right, so that's it. It was pretty long, but my hope is you take time out to watch this and it will make some sense. Now, if you're in the live session, you can ask questions. If you want to watch this over again and you have questions, you can drop the questions in the Telegram channel and I will engage with that.
Okay, thank you so much. So you are going to drop the notebook too?
Yes, you would see it as a part of your access to the resources you have for data science mentor. You'll receive it there.
All right, thank you.
Welcome.